Hello, welcome to today's class. In this video we shall be talking about psychrometric processes. In our previous class we explained the concept of psychrometry, and psychrometry is the study of atmospheric air, which is a mixture of pure air and water vapor at atmospheric pressure. In today's class we shall be looking at the different types of psychrometric processes. The chart here shows the different types of psychrometric processes, which we shall be explaining in this video. So for an horizontal line on the psychrometric chart, as you can see, it is humidifying and dehumidifying. When the lines are going up, it is humidifying, and when it is going down, it is dehumidifying. For the horizontal lines going towards your right, it is sensible cooling or sensible heating, When it is going towards your left, it is sensible cooling, and when it is diagonal towards your right, it is heating and humidifying, and when it is diagonal towards your left and going downwards, it is cooling and dehumidifying. We shall be explaining some of these psychrometric processes and looking at one or two calculations in this video. So the first psychrometric process we shall be looking at is sensible heating and cooling. Now, what is sensible cooling? Sensible cooling is carried out by passing air over the coil. During sensible cooling process, the dry bulb temperature and wet bulb temperature of the air reduces, while the latent heat of the air and the dew point temperature of the air remains constant. So the sensible cooling line can be shown on the psychrometric chart by horizontal lines going towards your left. So this line here is showing you a sensible cooling process. It goes towards your left. This is an example of a sensible cooling process. Now, what about sensible heating? Now, what you are seeing on the graph, when the line is going towards your right, it is known as sensible heating. Sensible heating process is opposite to sensible cooling process. In sensible heating process, the temperature of air is increased without changing its moisture content, as you can see on this chart. Okay, during this process, the dry bulb temperature and the wet bulb temperature of the air increases, while latent heat of air and the dew point temperature of the air remains constant. So we can carry out sensible heating process by passing the air over the heating coil. So that is how we can carry out the sensible heating process. So this line going towards your right is sensible heating. This is sensible heating. while the line going towards your left is sensible cooling. Sensible cooling. All right. Now, before we continue, I want us to note some important equations as it relates to sensible heating and cooling. The first thing I want us to note is that for a sensible heat, or when a sensible heat is less than 0, this is known as cooling. All right, and when a sensible heat is greater than 0, this is known as what? Heating. That's one. Number two is that latent heat, when latent heat QL is less than 0, this is called dehumidification. That is known as dehumidification. Dehumidification. And when latent heat transfer QL is greater than 0, it is called humidification. So please, let's remember this. Humidification. Now, we can be asked to find the rate of heat transfer, or the total rate of heat transfer for a system, and the formula is given as Q state 1 to state 2 is equal to the mass flow rate of dry air, is the mass flow rate of dry air, open bracket, the enthalpy at the exit, I call it H2, minus the enthalpy at the inlet. So here is an equation we can use to find the total rate of heat transfer. Now, you note that we have two state points. This is our state 1, and here is our state point 2. So to get your H1, you have to find the enthalpy at state 1. This gives us your enthalpy at state 1. Then to find your enthalpy at state 2, you use your state point 2, you draw your enthalpy line. This gives us our enthalpy at state 2. Now, to find our mass flow rate, we can use the formula which states that the mass flow rate of dry air is equal to cubic feet meters times 60 divided by the specific volume at state 1. So if you missed our videos on how to use the psychrometric chart, you are advised to click the video above to see how we find or use the psychrometric chart, so we can get our specific volume from state 1. So as a point of reference, I'm saying that your m.dA is the mass flow rate of dry air, the H2 is the enthalpy at the exit, the H1 is the enthalpy at the inlet, and the V1 is the specific volume at the point or at state 1. So our MdA is the mass flow rate of dry air, the mass flow rate of dry air, and it is measured in kilogram or kilogram per second, kilogram per dry air per second, or is measured in pounds per dry air per hour. All right, so that is for the mass flow rate. For the H2, our H2 is the entropy at the exit. The entropy at the exit. You can find the unit on the chart, which is BTU per pounds dry air. So our H1 is the entropy at the inlet. You can say at the entrance, at the inlet. All right. While our V1 is the specific volume at state 1, or at the inlet is the specific volume at state 1 or inlet. So these are basic formulas we can use when we are solving questions for sensible heating or cooling. So in summary, we are saying that sensible heating or cooling is the increase or decrease in temperature without changing humidity ratio. As you can see on the chart again, it is what horizontal, which means that our humidity ratio is constant. And I want us to note again that condensation occurs when the dry bulb temperature is below the dew point temperature. So the second psychrometric process we shall be looking at is heating and humidification. Now, in heating and humidification, the dry bulb temperature as well as the humidity of the air increases. That is very important. And also, the heating and humidification process is carried out by passing the air over a spray of water, which is maintained at temperature higher than the dry bulb temperature of air, or it can be done by mixing air and steam. So the heating and humidification process is represented on the psychrometric chart by an angular line that starts from the given value of the dry bulb temperature and extends upwards towards the right. So this is a sketch of the heating and humidification process. Now we have some formulas for this process. For example, we can be asked to find the change in total entropy. The change in total entropy which is equal to the entropy at the exit, which is H2, minus the entropy at the inlet, H1. Also, we can also be asked to find the change in sensible entropy. The change in sensible entropy, this is equal to H, or the entropy, minus the entropy at the inlet, which is H1. Now you'll be wondering, how do I get these values? So as you can see on the chart, we have two state points. Here's our state point 1 and here's our state point 2. So to get my entropy at the inlet, I will draw a parallel line on my chart that is parallel to the entropy lines. So this gives us our H1. To get my H2, I do the same thing, draw a parallel line to my entropy lines. This gives us our H2. Alright, now to get my H, I have to draw two lines from state 1 to state 2. So the point of intersection, I will take up a line and a pencil. I will draw a straight line that is what parallel to the entropy lines to my entropy reading. That gives me now what H. So with these we can find our change in total entropy and the sensible entropy. So the next type of psychrometric process is cooling and dehumidification. Now this is the opposite of heating and humidification. Now the process in which the air is cooled sensibly and at the same time the moisture is removed from it is called cooling and dehumidification process. Now cooling and dehumidification process is obtained when the air at the given dry bulb temperature and dew point temperature is cooled down below the dew point temperature, as you can see on this chart. All right. Now, the cooling and dehumidification process is most widely used air conditioning water application. It is used in all types of window units, split unit, packaged and central air conditioning systems for producing the comfort conditions inside the space to be cooled. So this is another very important psychrometric process. All right. So the next type of psychrometric process is called the adiabatic, or we call it the evaporative cooling. All right. Now this is a psychrometric process that involves the cooling of air without heat loss or heat gain. Now sensible heat lost by the air in this case is converted to latent heat in the added water vapor. All right. So how can we, or where do we apply this process? Adiabatic process is used in both biological and mechanical processes. For example, our bodies are designed to sweat to release heat and keep our body at its natural temperature when it gets too hot. Now you know that our skin releases sweat, which contains water. The water absorbs the heat from our skin and it eventually evaporates, taking the extra heat in our skin with it. This decreases our body temperature and keeps us from overheating in the summer. Now I want us to also note that JSCE uses this process to decrease the temperature inside a building. And also again, we must note that adiabatic process is used to cool nuclear power plants. So this is another very important psychrometric process. Let's look at another very important psychrometric process, which is called the adiabatic mixture of two air streams. Adiabatic mixtures of two air streams. As you can see on the chart, we have two state points. This is the first air condition, and here is the second air condition. And these two air conditions, they mixed and they give us what? A new air condition. Now, when two quantities of air having different entalpies and different specific humidities are mixed, the final condition of the air mixture depends upon the masses involved and on the enthalpy and specific humidity of each of the constituent masses which enters the mixture, and this forms our final condition, because at the entry point this has a different enthalpy. As you can see, this is H1. This has a different enthalpy which is H2. All right, now they also have what different what specific what humidity. Now when they combine, we have what a new condition which we call what H3. This is called H3. All right, so I shall be showing us formulas that we can use to find the conditions of the new or of the mixed air. So here will give us our new humidity ratio. Okay, so we will look at some formulas of how we can use this process to find the new or final condition of the air. Now many AC requires the mixing of two air streams, as you can see on this diagram. Here is the first air stream with different properties, and here is the second air stream with different properties. So they enter the system and are mixed to produce a new air condition. Right? This is particularly true for large buildings, production, and for process plants, and for hospitals, which require that the conditioned air be mixed with a certain fraction of fresh outdoor air before it is processed and routed to the building spaces. So mixing is accomplished by merging the two air streams, as you can see from this diagram. So from this diagram, which is similar to continuity equation, we can therefore say that that the mass flow rate of dry air times our enthalpy at point 3 is equal to the mass flow rate of dry air at point 1 times H1 plus the mass flow rate of dry air at state 2 times H2. We can do the same for the humidity ratio, and please note that this is called our energy equation. It's called the energy equation. All right, now knowing this equation, we can derive formulas for our new enthalpy, humidity ratio, and even for our dry bulb temperature. So when we transpose this, and please note that this is mass flow rates at point 3, and you must note that the mass flow rates at point 3 must be equal to the mass flow rate at point 1 plus the mass flow rate at point 2. So when we transpose this equation, our new condition for the enthalpy H3 will be equal to the mass flow rate at condition 1 times H1 plus the mass flow rate at condition 2 times enthalpy 2 over the mass flow rate at state 1 plus the mass flow rate at state 2. So this gives us our final condition for the enthalpy. We can also use a similar condition or similar equation for the humidity ratio. Becomes W3, which is humidity ratio, is equal to the mass flow rate at condition 1 times humidity ratio at point 1 plus the mass flow rate at condition 2 times the humidity ratio at that point over the mass flow rate at condition 1 plus the mass flow rate at condition 2. We can also use the same formula to get our dry bulb temperature. So for our dry bulb temperature, let me call it T is our dry bulb temperature. T3 is equal to the mass flow rate at point 1 is times the dry bulb at point 1 plus the mass flow rate at point 2 times the dry bulb temperature at point 2 over the mass flow rate at point 1 plus the mass flow rate at point 2. So with these we can solve for the new condition for the dry bulb temperature, for the enthalpy, and for the humidity ratio. Please note that this is the dry bulb temperature. Dry bulb temperature. Right. So this is our enthalpy and this is our humidity ratio. So in summary, we can say that adiabatic mixture of air is when two air streams are mixed adiabatically without or addition or extraction of heat, e.g., or for example, outdoor air mixed with a portion of return or recirculated air. That is a basic concept of adiabatic mixture of air. Now let's look at questions as it relates to psychrometric process. The first question here is this: we are asked to find the rate of heat added to a room if the moist air at 60 degrees Fahrenheit and 100% relative humidity enters a heating coil at 175 cubic feet per minute. In this case, we are given the inlet condition. So this is our inlet condition and it's leaving at 95. This is our exit condition. So we are asked to analyze the type of psychrometric process. Before I can do this, I would like to plot my chart with the given information so as to know the type of psychrometric process. But first, I want to write out my given conditions. So let me call this point my inlet conditions. Here's my inlet conditions, and right here is my outlet conditions. All right. So for my inlet conditions, I'm giving it that moist air at 60 degrees Fahrenheit, which is my dry bulb. So I can call it my dry bulb T. My dry bulb is equal to 60 degrees Fahrenheit. Remember that we have to have two state points. So we are giving two different conditions. The inlet is the first state point, while the outlet is your second state point. So we are giving 100% what relative humidity. So my RH is 100 degree or percent. Yeah. Now we are given the CFM. So my CFM is giving us 175. Remember that we have to use this. Then for the outlet, it lives at 95 degrees Fahrenheit. That's my dry bulb temperature. It is at what 95 degrees Fahrenheit. So I can call this my dry bulb temperature 2. Here's my dry bulb temperature 1. So T is our dry bulb temperature. All right. So before I continue, let me look at my chart. So the first condition, I'm giving dry bulb at 60 and RH at 100%. So I'll come to my chart and try to get my first state point. It says that my dry bulb is at 60, so here's my 60. Okay, here's my 60. I draw the line up, my 60. Okay, that's my 60. I can make the line visible. Make my line visible, good. That's my 60. Now it says my relative humidity is 100, which is given as, yes, 60, 70, 80, 90, 100. So this is my 100. So I can take my pencil again and draw a curve on that point. So here is my 100. So okay, so this is my 100. Yes, all right, good. So that is my 100. So the point where these two lines intersect is my first state point. So this point right here where the 60 and the 100 intersect is my first state point. So it's very important for you to label that. So here is my state point 1. So I call it my state point 1. So that's my state point 1. All right, now back to the question. It says it leaves at 95 degrees Fahrenheit, which is my dry bulb temperature 2. So that means that at the same humidity, because as you can see it is saturated, it leaves. So I'll take my pencil again, take my pencil from, I will take my pencil at 90, at 95, that is my my exit point, which is 95 right here. I'll take my pencil, I will draw a straight line at 95, make it visible, good, make it visible. All right, so it leaves, so from state point 1, it leaves the system at 95. So this is the point where it intersects with the exit. So that point is my state point 2. So let me take a different marker. So this point is my state point 2. This is my state point 2. So I call this point my state point 2. So now I have drawn my sketch. We have to show the sketch even in our exams. So this is my state point 2. Good. Now from this sketch of my chart, I can see that the line is going from left to right, and that tells me that it is a sensible heating. All right, it is a sensible heating. So I can use the formula for the, so because we're asked to find the rate of heat added, so I can use the formula, which is the rate of heat added from point 1 to 2 is equal to the mass flow rate of dry air times the enthalpy at the exit minus the enthalpy at the inlet. Now remember, we have to find these different values. Step 1, to find my mass flow rate, I know that my mass flow rate of dry air is equal to the CFM times 60 divided by the specific volume at state 1. So here I have 3 unknowns. My CFM is given to me right here, but my H2, H1 and V1 are given, so I have to find that, I have to find those values. So and to find those values I have to find them from my chart. So to get my H2 and my H1 and my V1 from my chart. So to get my H2, I used my state point 2. Come back to my chart. Yes, my state point 2. To get my H2, I get it from my state point 2. I take my ruler, I draw a parallel line from the state point to my enthalpy readings. As you can see, that gives us 35. As you can see, so my enthalpy H2 is 35. So you can come here and write it down. So enthalpy H2 is 35 BTU per pounds dry air. All right, come back to my chart for my H1. To get my H1, I use my state point 1. Again, take your ruler, your pencil, you draw a straight line or a parallel line to the enthalpy lines from the state point 1. Look at this, you draw a parallel line. All right, so for my state point, I draw a parallel line. Good. All right, so that is my H1. That is my H1. So this is my H1, and here is my H2. Okay, so for my chart, my H1 falls between, this is 25, okay, this is 26, this is 27, 28, 29, 30. So my H1 falls between 26 and 27. So that I will call that approximately 26.5. So my H1 is 26.5 BTU per pound dry air. Per pound dry air. Now for my volume, from the chart I can get my volume. As you can see, here is my 13.0. So what you do is that you take your pencil and your ruler, you draw a line that is parallel to the volume lines. Remember, your volumes are these diagonal lines. So we have 13.0 right here. So I will take my pencil for my state point, I will draw a parallel line to my volume line, as you can see right here. So this is my my V1. So that is my V1. So here is my V1. Okay, so as you can see from the chart, here is 13.0, here is 13.1, here is 13.2, 13.3, 13.4, 13.5. So my V1 falls between 13.3 and 13.4 and is closer to 13.3. So I can score this approximately 13.35, or let's say 13.33. So our V1 is 13.33 cubic feet per pounds dry air. So now I've gotten my values from the chart. So what next is to solve our equation. So therefore we put in our values. So therefore our mass flow rate is equal to, CFM is 175, so we have 175 times 60 divided by our V1 is 13.33. So if you put that in your calculator, our mass flow rate of dry air, it gives us 787.7 pounds per dry air per hour. So we have 787.7 pounds per dry air per hour. So that is our mass flow rate. So therefore our rate of heat that was added to the room is, mass flow rate is 787.7 times our enthalpy at the exit is 35 minus enthalpy at the inlet is 26.5. So therefore we have 787.7 times 35 minus 26.5, that gives us 8.5. So therefore 787.7 times 8.5 gives us 6695.45. We have 6695.45 joules. So that is our heat added to the what, to the whole. So we can convert this to kilojoules. It becomes 6.7 kilojoules. This is our final answer. Remember again, you can leave your answer in BTU, right? So it can also be in BTU. All right, so here is another question. We're asked to determine the dry bulb temperature and wet bulb temperature of the resulting mixture of a stream of 0.45 pounds per dry air per hour of outdoor air at 40 degrees Fahrenheit dry bulb temperature and 35 degrees Fahrenheit thermodynamics wet bulb temperature is adiabatically mixed with 0.55 pounds per dry air per hour of recirculated air at 75 degrees Fahrenheit dry bulb temperature and 50% relative humidity. As you can see, this is very obvious. It is adiabatic mixing of two air streams. So I would like us to write out our given conditions. In this case, we have two conditions. We have the condition 1, let's call it condition 1, and we'll call the other one condition 2. So here's my conditions 2. All right, cool. So for my condition 1, I'm giving the mass flow rates, so I can take them my parameters. We are giving the mass flow rate at condition 1. Let's call it mass flow rate at condition 1 is giving us 0.45 pounds dry air per hour. Okay, we are giving the dry bulb, let's call it call it T1, is giving us 40 degrees Fahrenheit. All right, and also we are giving the wet bulb, let's call it TW1, is giving us 35 degrees Fahrenheit. Okay, so is adiabatically mixed with 0.55. So here is the second air stream, so we call it mass flow rates of dry air for condition 2 is giving us 0.55 pounds of dry air per hour. We are given dry bulb temperature, let's call it T2 is 75 degrees Fahrenheit, and here we are given the relative humidity, let's call it RH2 is giving us 50%. Now with these conditions we can find the final condition of the mixed air, because in our question we have to find the dry bulb temperature, so we have to find T3 and the wet bulb temperature, so we have to find TW3. So these are our unknown. This is our new condition, or I can say is our final, let's call it our final condition. Final condition. So to find the final condition, I gave us formulas earlier that we can use to find the final condition. So for us to find the final condition for the dry bulb temperature, the formula is this: is T3 is equal to the mass flow rate of dry air at condition 1 times T1 plus the mass flow rate of dry air at condition 2 times T2 is divided by the mass flow rate of dry air at condition 1 plus the mass flow rate of dry air at condition 2. That we can use to find the final condition of the dry bulb. Also, for the wet bulb temperature, we can use the formula, which is a similar formula to this. Is TW3 is our wet bulb temperature, is equal to the mass flow rate of dry air times at state 1 times the wet bulb temperature at state 1 plus the mass flow rate of dry air at condition 2 times the wet bulb at condition 2 divided by the mass flow rate of dry air at condition 1 plus the mass flow rate of dry air at condition 2. So with this we can solve for our final condition. And please, I want you to note that before you do this, you have to look at and see what is given to you, so that we can know what we are to look for from the chart. Now, if I look at this equation here, my mass flow rate at state 1 is given to us, our dry bulb at state 1 is given to us, mass flow rate at state 2 is given to us, our dry bulb at state 2 is given. Alright, so we have all these ones right here. Now for this, our mass flow rate at state 1 is given, our wet bulb at state 1 is given to us, mass flow rate at state 2 is given to us, but we're not given the mass flow rate at state 2. So the first thing we have to do from the chart to solve this question is to look for our mass flow rate or our wet bulb temperature at state 2. So to do that, we have to plot the chart for these two conditions. Let's start with the first condition. We have dry bulb as 40 and we have wet bulb as 35. So I come to my chart. Remember, we have dry bulb as 40. So take a pencil. Dry bulb is 40. So this is the dry bulb line. Okay, these vertical lines are the dry bulb lines. So at 40, yes, 40. Draw my line at 40. Yes, that's 40. Good. So make my line visible. Good. So our wet bulb is 35. So take my, these faint vertical lines are 35. Look at these lines. You can see them. These faint lines are 35. Wet bulb lines. So here's my wet bulb line. So I can draw my wet bulb lines. Good. So that is my wet bulb line. All right. So that is my wet bulb line. Now, this is my state point 1. All right. This is my state point 1. I can call this, I can label it. This is my state point 1. It's very important to show your state point. So here is my state point 1. All right. Now for the second condition, which will help us to find our wet bulb at state 2. We are giving the dry bulb as 75 and the relative humidity as 50%. So come back to my chart. We have dry bulb as 75. Take a pencil again. This is dry bulb here at 75. You draw a straight line up. This is dry bulb line at 75. Make my lines visible. Then they are giving the relative humidity as 50%. Again, take a pencil and make your lines neat. This is 50% right here, so I can draw my curve. Here is 50%. Yeah, that's 50%. Good. That's 50%. So I can take my pencil and label my work. So this is my state point 2. That is my state point 2. So I will label it. That is my state point 2. So here is state point 2. Good. Now these two air are going to mixed adiabatically to give us our final condition, which we can work out using the equations above. So we have to find our wet bulb at state point 2 because that is the only unknown from my equation. So come back to my chart. Remember guys that the wet bulb lines are the faint diagonal lines. As you can see right here, they're the faint lines. So I will draw a parallel line to the faint lines to my curve. That line is my wet bulb line. Let me make it visible. All right, so this line here is my wet bulb line. I can call it my my TW2. So as you can see here, this is 60, this is 61, 62, 63, 64, 65. So I can call that, I can say that my wet bulb line is 62.5. So my wet bulb line at state 2 is 62.5 degrees Fahrenheit. All right, so now we can solve for our final condition, and when you finish solving, you can show this condition on your chart if you want to do that. So for my final condition for my dry bulb temperature, I put in the values. So we have is equal to, and mass flow rate at state 1 is 0.45. So I have 0.45 times my T1 is 40, my dry bulb 1 is 40, plus the mass flow rate at state 2 is 0.55. So here is 0.55, and my dry bulb at state 2 is 75 over mass flow rate at state 1 is 0.45 plus the mass flow rate at state 2 is 0.55. So that gives us 0.45 times 40 will give us 18 plus 0.55 times 75 will give us 41.3. Divide by 0.45 plus 0.55 give us 1. So therefore my final condition for my dry bulb is 18 plus 41.3. That gives us 59.3. That gives us 59.3 degrees Fahrenheit. Approximately, I can call that 59 59 degrees Fahrenheit. Alright, so my final condition for my dry bulb temperature is 59 degrees Fahrenheit. Okay, let's look at our final condition for our wet bulb temperature. So again, we log in the values. The mass flow rate for state 1 is 0.45 times the wet bulb temperature at state 1 is 35 plus the mass flow rate at state 2 is 0.55 times the wet bulb at state 2 is 62.5. Divide this by mass flow rate at state 1 is 0.45 plus the mass flow rate at state 2 is 0.55. Alright, let's go. So 0.45 times 35 will give us 15.75. That's 15.75 plus 0.55 times 60.5 gives us 34.38. So we have 34.38. Divide by 0.45 plus 0.55 gives us 1. So therefore, our final condition for our wet bulb 3 is 15.75 plus 34.38 gives us 50.1 degrees Fahrenheit. 50.1 degrees Fahrenheit. So I can call this approximately 50 degrees Fahrenheit. So this is our new condition. Now we can decide to show this on our charts because again now we have a new condition. So my new condition, we have dry bulb as 59 and wet bulb as 50. So I can come to my chart. Okay, my chart. I take my pencil again. My dry bulb is what? Is 59. So here is 55. Here is 59 right here. Okay, here is 59. Draw my line up. Okay, and use a black line. Okay, then my wet bulb is 50. Take my pencil. Wet bulb is 50. This is my 50 line right here. Look at it, the front line. My 50 line is the front line. Got it? Yeah, that's my 50. The front line, that's my 50. So here is my state point 3. So this is my state point 3, or I'll call it my final condition. So here is my final condition. I call this my final condition. Now at that point is where the two air streams we mixed adiabatically. So here's my final condition. All right, so now these two air streams are going to meet at that point. That is what we call adiabatic mixture air. So in state 1, the fourth air stream will meet at this point. Okay, let me use a different marker. Okay, while state 2 we also meet at this point. All right, so this is what we call adiabatic mixture of two air streams. So this is our final answer to this question. So you can see that we have to show our workings on the psychrometric chart, and for your exams you are advised to do the same, to show your lines and your state points and even the final condition for adiabatic mixture of air streams on your chart.